Hello there, and welcome to another live stream with me, Simon, from the Redis Developer Relations team. It's been a little while, and normally I would be doing IoT type projects, but today we're going to do something slightly different. We're going to look at something with maps and polygons and searching, and we're going to look at something that was added in a recent Redis release. So I'm just going to share my desktop and basically dive right in. So what we've got here is we recently announced the release of Redis 7.2, which had a whole load of features across a range of things. Today, I'm going to focus on one specific area, and that is the search capability of Redis Stack. And we're going to focus on a specific thing that does that was actually called out in this blog post. So if we sort of scroll down a little bit here, you'll see we did some AI stuff. We did some developer-focused stuff. We added triggers and functions, which is a whole other area that we'll be talking about on this team in the very near future. But what I wanted to do was focus on some of the geospatial in Redis Stack. So what you see here is that we added Polygon searches, and we will sort of look through what that means. But basically, what it means is we can now do what points of interest are within a shape that is not a circle and a radius, but is a complex polygon. So like, which of my stores are in the state of California or the city of San Francisco? And we can also do things like represent those points of interest as polygons themselves. So they don't have to be an XY specific point, which might make sense for example, some of the things on here. So Coit Tower is a specific location. If we got something that was like a longer point of interest that we might walk along, like the Embarcadero here in San Francisco, that's kind of like a long, thin polygon that wraps around that water's edge there. So we'll look at that sort of stuff. I've got some code that is in both Python and Node.js, but you don't have to be particularly proficient in either of those to follow along. And we're also going to do some stuff at the command line to see how the commands work. So first off, what we're going to need to do to get this working is, this is Redis 7.2 Stack. We're going to need a 7.2 Stack database. So what I'm going to do is, let's get rid of the blog post here. I'm going to go over here to redis.com, and you would, if you're new, you'd hit try free and sign up. I'm going to get a free database with an existing account, so I'm just going to hit login. And I'm going to log in with my credentials here. That's, hopefully you remember the password. There you go. So I've got nothing in this account at the minute. It's completely empty. So you can get 7.2 Stack on Docker as well, but we're doing it in the cloud because it allows us to connect lots of things to it from different places. It's free, and obviously there's nothing to install. So I'm going to click Create Subscription here. And what you see here is we have different types of subscription. If you want bigger things, you can pay for those. We're going to go straight down here over to, in the fixed plan, there's a $0 option, which is basically 30 megs of Redis. That is no charge. And then what I need to do is make sure that I want the 7.2 preview. So it's still kind of early days for this in the cloud. So if I turn that on, it's going to then show me what regions in each cloud it's available in. So it's available in AWS in those places and Google Cloud in these places. And as we continue to roll that out, that will obviously improve and become across everywhere. So I'm going to pick, I don't know, let's do US East Ohio. Why not? I'm going to pick there, and I'm going for the standard 30 megabytes, which, as you can see, is not going to cost me anything. So I don't need to put any payment details in. I'm going to create a subscription. Oh, I have to give it a name. So let's call it live stream. Create a subscription called live stream. And in there, there's absolutely nothing at the minute. So I need to create a Redis database in there. So let's do new database, and we'll call it Polygon demo. And I want this one, Redis Stack, because I'm going to be using the search features of Redis Stack. I really don't need anything else here. I just need to, at some point, know the password, and we'll be pasting that into Redis Insight so we can connect to the database. But that's it. So I just basically need to give it a name, select Stack. So once we've done that, I can now click Activate Database. And you'll see here I have this orange pending clock. It's off building the database. And at some point in the very near future, that should go green. And there we go. It's gone green. And we should be ready to connect. So we now have an endpoint here. So we need like a couple of things to connect to this. So we need a host and a port. So that's this long string here, and the port is 14847. And then we need a password, which is down here in the security section. And we'll use the default username. We're not going to create access control users or anything for this simple demo. So what I've got to do now is connect to this database. Let me start doing something with it. So I am going to take this information here and copy it. I'm going to start up Redis Insight here. So Redis Insight is a visual tool for managing Redis, and you can download it for free from us. And I have a banner for that somewhere, probably. There we go. Download Redis Insight. So you can download Redis Insight and install it, and you can connect it to multiple instances of Redis. So I have a couple here already. I'm going to add this new one that we just created. So I need the host, and if I paste that in there, what actually happens is a little bit intelligent. So I had the host : the port, and it stripped the port off of here and put it down here for me, so I don't need to go back and get that. We'll call this Polygon demo, give it a nicer name. Then our username, remember we were going with default. And I need to go get the password from the cloud. So let's go back here, down to my security section. I can either reveal it, but let's not do that. Let's copy it. And let's paste it into the password field there. And hopefully when we click add Redis database, it's going to try connecting to it, and we're good. We're connected. So we've been on stream, 10 minutes, and we have already got a 7.2 Stack database in the cloud. And you can see it there. It's called Polygon Demo. I'm going to click on it, and we're here in the key browser. And as you can see, we're in a sort of start wizard state because there's nothing in the database. So it's completely empty at this point. So what I wanted to do was first sort of talk about what was in the search capabilities, geo capabilities before this release. So what could we do prior to 7.2? And then sort of go on to what can we do now we've got these extra capabilities. So in order to do that, I'm going to go to the workbench here in Redis Insight. And one of the things you'll see here is we have these tutorials, and you can make your own as well. They're basically just markdown documents that you can upload into this tool. So if you have like sets of commands or things or data that you want to share with other team members, you can put them in here and have a sort of source of that. So I created a little one here called Polygon Search. And when I click on this, there's some markdown formatting that basically allows me to build a sort of table of contents. And then when we click on one of these things, what will happen is some Redis commands will appear over there on the right in the workbench. So to demonstrate what's kind of always been there in search, I've got some points of interest for Sydney in Australia. And we wanted to see if we could do some searches against those. So if you're new to the search capability in Redis, it gives you sort of SQL-like querying over a key value data store, which is quite powerful because normally with key value data stores, you need to know the key in order to get the data out. So if we stored our points of interest as, Sydney : Opera House or something, and you didn't have Opera House, then how else are you going to find the Opera House? Search solves for those sort of issues and provides the speed of Redis with the flexibility of SQL-like querying. So we'll see how that works. So over here, I've got, when I press this button, it puts a load of commands in the sort of workbench area here, and they've not been executed yet. So I can send them to Redis by hitting that green play button over there. But before we do that, let's look at what we've got here. So what I've got is I'm using the hset command. I'm going to use a Redis hash, which is a sort of flat map of name value pairs that live under a key in Redis. And we're saying we're going to use key names such as Sydney, colon, and then the attraction name. And I've replaced the spaces with underscores just so it's a bit easier to type. So we've got Sydney, Bondi Beach, and then I'm storing two things about that. I'm storing name, which is a string, and then the location, which is a longitude, comma, latitude point on the globe. So we've got all of these, and the way that search works is it works over data in Redis that's stored in one or two data types. So one of those is the hash that we see here. The other one is a JSON document that we will look at in another example. But essentially, search works pretty much the same. It's just how you tell it where to find the data in the documents that differs. So if I hit play over here, what happens is it goes off and runs all of these commands, and you'll see they all returned integer 2. So what that means is my hset command returned 2. It set two things inside the hash, so name and location, and each of those were successful. So if we just quickly go over to the key browser here, what we'll see when we refresh this is we've now got all of these hashes in here, so we can pick on any one of them. So let's look at, I don't know, Luna Park. And what you see inside this single key Luna Park in Redis is like a small name value pair map. Name is Luna Park, and the location is longitude, comma, latitude, the values that we had in the command. So there's no schema going on here. This is schemaless. It's we've just set a convention that everything has these fields. So we could quite happily add another field in here and call it something like entry price. And we can say it costs, I don't know how much Australian dollars are worth these days, but let's say it costs $9.50 to go into Luna Park. We haven't broken anything here. The other attractions don't have any of these fields. They don't need them. It's not a SQL table. So it's not going to break anything. It's just schemaless. These are allowed to be different. So we could, for example, also pick the harbor beach here and add another field and call it like swimming and put yes, swimming's allowed. And then we could pick Bondi Beach and we could add a field surfing, and surfing is allowed, assuming the weather's good enough or sea's not too rough. And none of this really matters that the other things don't have that. So we've got that. And then just sort of quick pre-search demo. Normally without search, if we wanted to get the details for Bondi Beach, we would do something like hget all. So we'd say, get me everything in the hash, Sydney, Bondi underscore beach. And what you get back is the things that are in there. So you can either get all of it, or you can use something like hget Sydney. I've been away from this keyboard for a while. Bondi Beach, and we could say, just get me the surfing field, and then you're just going to get true. So that's roughly how hashes work. So how do we answer questions like, well, what's nearby a given point? Or what attractions have bridge in the name? You kind of can't with this setup without some additional capability. And that's where search comes in. So what we're going to do is add some search, and we are going to create a search index to start with. So comment, can I increase the font a little bit? Probably. It kind of makes things a little bit narrower, as in we lose some columns, but let's see. Hopefully that's a bit better. So we've got these hashes. We can access them by key. What we need to do is go back to our workbench, and we're back to here. And then our next command that we wanted to do is create a search index. So with search, we need to tell it what things in those hashes we're interested in. And if they don't have them, then we're not going to be able to search on them. If they do have them, great. We are not going to break anything by having this sort of differential schema. So what I'm going to do here is I use the ft.create command. So all the search commands begin with ft for full text. And I'm going to create a search index. So I'm going to call it IDX:Sydney because it's searching for things in Sydney. And we tell it what data type we're going to want it to focus on. And we're going to want it to look at hashes because that's where we stored our data. And then we tell it which parts of the key space. So we're going to say keys that begin with the following one prefix, Sydney:. So anything else that we put in Redis in a hash that begins with, like, say, Melbourne or Adelaide or Alice Springs or wherever is not going to be part of this index. So that helps with performance and also with if we wanted to index different parts of the key space differently. Then what we have to do is tell it how to index things. So we have a schema, and then the schema is a series of names and data types. So we're saying that the field called name, so the name of the attraction, we want to index as a text field. So that's for full text search. And then the location we want to index as geo. So that basically says expect that to contain a longitude, latitude value, and then we'll be able to do some sort of geo searches on it. So if I create this, you'll see it says, okay, so it's gone back and indexed those documents. And what happens now is every time we change one of these documents or add one or delete one, the server will keep track of that for us automatically. So we do not need to run a re-indexing process. And because everything's in memory here, it'll do that extremely quickly. So once we've done searching or setting this up, we want to do some searches. And the two things that we can search by, because they're the two things that we indexed, are name, and we index that full text. So we can do some sort of fuzzy or partial search on it. And location. So we can do what's near me. And previously to 7.2, the sort of searches that we could do were this sort of thing. So we could basically say, let's do a search in the Sydney index, and I want values or indexed items where the location field is within a 4-kilometer radius of this longitude, latitude that I'm providing. So that's actually Sydney rail station, so Central Rail Station in the middle of town. So we are saying, tell me what's within 4 kilometers of there from the hashes that are in the index. And then we're telling it what we want back. So we just want it to return one thing, and that's the name field. So it's a little bit like where I ran the hset command, sorry, the hget command, rather than the hgetAll. So we're limiting what comes back to just the thing that we need. And then we're telling it how many results we want. So I want the first 100, and we can paginate through those if there's loads. And obviously here we'll have less than that because we only had 8 or 9 attractions. So if we go ahead and run this command, what you'll see is a couple of things. We get some results, and Redis Insight makes a nice table of them for us. So it's kind of helping us understand those results in the workbench. So what you can see here is that these are the keys that match. So the search treats everything that matches as a document. So this is the document that matched. And this is the field that we asked for, the name of it. So all of these things are within 4 kilometers of the Central Rail Station. And then if we ask it some more questions, like drop this to maybe 2 kilometers, what you'll see is the only thing within 2 kilometers of the rail station is the cricket ground. So those two things are relatively close to each other, and the rest must be further away. So we can do this, and I'll just show one more thing. Let's remove, what happens if we remove this return clause? We'll get everything back. So what you get now, look, is everything, and Insight has attempted to make a table of it. And what it's done is, because not every value has the same schema, it's just made a table, and some of these are blank. That field doesn't exist. It doesn't have to exist. We're not indexing it, so it doesn't matter. So you get this extra swimming and entry price column here, and the only attractions that have those are the ones that we modified to have those things. So that's all very good. We can do a basic, like, what's near a position. So, what's near the station, these things are. we might be a little bit more discerning about how we want to explore Sydney. So we might be like, you know what, I've come to photograph bridges and I'm at the railway station. So what bridges are near to the railway station? And because we index this name field as text, we could start looking there to see whether there are any bridges. So a simple query to do that would be this here. So what we're saying here is, again, searching the Sydney index. We're saying, find me things that have the text bridge in them. And we're not actually specifying which field in the hash that has to be in or which index field it has to be in. We're saying anything you're indexing that's got bridge in it, that will do. And then the location query is exactly the same. So now we're saying stuff within 4 kilometers of me that has got bridge in the name, and just give me the name of those things. So when we run this, we get both of the bridges. So we get Sydney Harbour Bridge and we get Anzac Bridge, but we no longer get like the Opera House or the aquarium or all the other things that were coming back when we ran this query down here. So this is, I'll bring it up again. This is essentially like an AND query. So we can do bridge and location within 4 kilometers. We could run arbitrarily complicated queries. So we could say, bridge or cricket and location within so many kilometers. We can change the kilometers to be miles and so on. So that's a run through of what geo things existed prior to 7.2 in search. So we could basically do some sort of radius searching around a circle. And I'm just going to clear this down a little bit now and shift gears into, clear all of it down. Shift gears into another example. So another thing that we might want to do is search for polygons, or basically shapes that aren't circles. So they might be rectangles, squares, arbitrarily complicated polygons. So the outline of a state or a voting ward area or something like that. And we might want those both as the thing that we are searching for. So the point of interest is itself represented as a polygon. So it might be like Central Park in New York has a very distinct shape. It isn't, a given point. It's got multiple entrances and all of that. And we might also want to search for, rather than saying I'm at the railway station, you might want to say I'm in New York State. And you might want to search polygon that is the shape of New York State. So in 7.2, we added support for polygons, and that works in a couple of ways. So we're going to look at some maps examples that are quite visual. But first, we're going to look at essentially an arbitrary polygon coordinate system. So I have actually created one of these via the magic of Google Sheets. As you can see, it's really, really complicated. It's a 20 by 20 square. So imagine we've just got a piece of graph paper, and if you used to build video games for old computers or something, you've probably seen this as a sprite sheet. You draw out your zeros and ones for where you want the pixels on or off. But imagine we've got some sort of system, like we're laying out a warehouse or an exhibition floor or something, where we've just created arbitrary coordinates. So ours start at 1 and they finish at 20, and the x-axis goes across the top and the y-axis goes down the bottom. So 1, 1 is this square in the corner, 2, 2 is this one, and so on. And what we're going to try and model here and show some of the new stuff is that we can store points of interest as polygons. So we're going to store these 5 polygons here. And what we are going to do with them is store them in JSON documents. They don't have to be JSON. They can be in hashes. And we're just picking JSON because it shows something different from what we did before with Sydney. And then we're going to search for these. And we're going to ask it questions like, is this point in this coordinate system within one of these polygons? Which one? And also, which polygon, if I provide a search polygon that looks like that or something, which point of interest is contained within that, or which point of interest wholly contains this search polygon? So we can do different stuff. So I'm not going to go through all of the how do we translate this into storing it in Redis, but basically what we are using is a standard called the well-known text format for geo representation, and it supports a few different shapes. And at the minute we support polygon and point, and we'll have a look at how those work, but I'll keep this over in the corner while we do. So if we go over here and click arbitrary coordinates demo, place polygons on a grid, what we'll see is I've got 5 JSON documents. So here's the first one. So if you're not familiar with the JSON capability of Stack, this adds the ability to store JSON documents natively in Redis. So we can store them, and then we can query them and get fragments out or update fragments atomically in place without having to pull the whole document back into the client, do some work on it, and then maybe someone else changes it on the server in the meantime. It takes all of that serialization and deserialization away. So I'm storing the same sort of information that we had for Sydney. We're storing a name, and instead of a lat long now, we're storing a geometry. And this choice of field name is pretty arbitrary. I could call it anything I like, but I called it geometry because that's what I'm going to store in there. So it just makes life a bit easier. And what we're storing in here is this here is a well-known text format representation of a polygon. So this isn't something that we made up here at Redis. It's a standard. And there are libraries in various programming languages to work with it. So what we've got here is the well-known text for a polygon is literally the word polygon. And then we have a couple of sets of brackets because in future we'll support this, but you can also add multiple distinct sets of points in here. So we could have a polygon with a hole in the middle. Imagine it was like a donut or something. And then each of these things in the inner brackets here is a set of points that form the edges of the corners of the polygon. So if we look at this one here, we've got where is polygon 1? Oh, it is the orange one. Okay. Polygon 1 starts at 3,2, so 3 across, 2 down, and then it runs to 12,2, which is this point over here. Then it drops down to 12,7, so we've got 12,7 and across to 10,7 and so forth. And eventually it comes back to here at 3,3. So what we need to do here is add all of the points that make up the sort of outer edge corners of that polygon. And then we have to close it. So what we need to do is then add the first one again. So that will close the polygon. And let's put that back. And what have I done? I think that's still valid. So what this does is it tells us how the polygon is to be represented. So we've done that for each of these things. Some of them are simpler than others. So the ones that are rectangles have 5 points. So remember, again, it's 1 for each corner essentially, and then the back to the start again, so it knows where it closes. And when I hit play on here, what you'll see is we've gone away and stored a load of JSON documents in the database. Nothing's happened to them yet because we haven't created an index. But what we can do is go back to the key browser here, refresh this. We should see that I've now got some keys that begin with a prefix polygon, and they are of type JSON. So if we pick on polygon 1 there, you'll see that Redis Insight has rendered that for me. I've got the name, polygon 1. I've got the geometry, which is what we put in there. Just storing this in a JSON document doesn't do anything with this well-known text. So it's not validated that that's correct or attempted to do anything with it. At this point to Redis, that's just text. It's completely meaningless to Redis. And just to sort of quickly show how this compares to hashes, if I bring up the CLI here and we'll do some equivalent commands. So you can see here before I was getting everything for Sydney out of the hash, and then I was getting just one field. So for JSON, I can do json.get Polygon :1, and then I need a JSON path. So $.name, and you'll see I get the name back. And I can do just give me everything, $, and then we get the object back. And you'll see that that's somewhat escaped here in the CLI, but client libraries for Redis will translate this for you into whatever an object looks like in your programming language. So Python, Node, whatever you're using. So we've got our data installed here, and we're using JSON documents this time. And what we need to do is go back to the workbench and look at how we're going to index this. So we click this. This time we're going to build a slightly different sort of index to what we had before. So there's two differences. First one is we're indexing JSON documents. So we're indexing JSON documents with, again, a single prefix, Polygon. And then here in the schema, we have to give it JSON paths. So I'm saying $.name, which is a field called name off of the root of the JSON. And I'm going to call that name in my index. And then I'm calling that a tag, which is essentially a complete text match. It's literally like a tag word. So Polygon 1, 2, 3, 4, 5, we could search for those, but we can't search for just Polygon like we could search for bridge in the Sydney example. No reason why this can't be text. I just wanted to show the differences. The implementation differences are that this allows for exact match searching rather than sort of fuzzy and partials. And this is a lot more efficient on memory. So if you don't need that more complicated matching behavior, then don't use text, use tag. If you do need it, use text. And what we're doing that's different here as well is we are taking that geometry field that's got the well-known text representation in. I'm calling it geometry in my index. And then this is different. So the Sydney examples where we had lat long, we were indexing those as geo. Here we're indexing them as geo shape, which tells the search capability to expect them to contain well-known text format. And we're saying flat, which is we've got a coordinate system here that we made up. The other option here, as we'll see later, is spherical, which is we're mapping it onto a ball, so basically the Earth, and we're using lat long type coordinates. So for arbitrary setups like this, we're indexing things with the flat coordinate and with the actual lat longs for real points of interest out in the world that we'll look at shortly. We're indexing it with the spherical one. So if I go ahead and hit this, you'll see again, it's come back with OK. And what happens again is that if those JSON documents change or new ones are added that match the prefix and have those fields, the index gets updated for us. So we don't have to worry about that. So what I'm going to do now then is look at the sort of queries we can ask of this index. So we go back to the visual of what these things look like. One of the things we can ask it is, does a given point, so if we're at point like here, does that point fall within a polygon? And if so, which one? So imagine we're building like the popular game Battleship or something. You could be like, I want to guess this coordinate here. Does that fall into one of my opponent's battleships? And search could tell you, yes, it does, or no, it doesn't. So let's see how that works. So here we go. So we're again going to the ft.search command. We're saying I want to search my polygons index. And we're saying I want to search in the geometry field. And at the minute, we support a couple of operators. So we support contains and within. So we're going to say, I want to know which thing that is indexed has a geometry field whose polygon contains whatever well-known text we're going to provide. So we're going to provide another bit of well-known text that is our search area. And we're going to say what in the database's geometry contains this. And we are basically saying, OK, we're going to pass this two things. WKT is like a variable. So this here is a variable. And what we're doing here is saying the value of the variable WKT, we're going to say is point brackets 11.3. So this means in WKT terms, a specific point that is in our coordinate system at 11.3. And if we have a look at this, 11.3 is one above the one I had selected. So it should be inside a polygon. And then what else have we got? We've got return one name again. So we just want the name back. And we've got this dialect 3 thing here. So the search query language has evolved over time. Dialect 3 basically allows us to use WKT geoshaped queries in our searches. When this is integrated into clients from your programming language, you won't have to worry about this because the client will add this for you as you're working with a higher level, more idiomatic approach in, say, Node Redis or Redis Pi or Jedis or whichever client you use. Let's go ahead and run this, and hopefully I didn't mess up the Polygon loading. Yep, there we go. So you'll see it's saying that 11.3 is in Polygon 1. So we've got a hit. Yeah, we've sort of thrown a dart into the board and we've found something. So this is different from what we had before. So we're not talking about radiuses now. We're saying basically, is this point inside this arbitrary area that could be quite complex and defined by quite a large polygon? That's one of the sort of queries we can do. The other sort would be, again, going back to the visual, if we wanted to define a search polygon area, so something like if we said, let's take that, so the whole bottom half of our coordinates area. So imagine this was a warehouse and like this bottom half is the ambient area and the top half is the chill area or something like that. We can ask questions like, which things in the database have a polygon that is entirely inside this other polygon area that we're going to provide in our search? And this could be arbitrarily complicated as well. So it could be any shape. We'll demonstrate that later when we move to maps. But for now, I'm just going to use a rectangle because it keeps the number of points down in the CLI. So what you'll see here is we're now saying, I want to do a search on the polygons index. Again, same thing, the geometry. This time we're saying is within, not contains. So what we're saying is what we're providing is a polygon that acts like a sort of mask over the coordinate system. And we're saying what in the database falls entirely within that polygon. That's entirely within. So intersects will be an option in the future, but for now it's within or contains. And again, we have to provide it some value for that WKT and well-known text. And we're saying, here's the polygon that we want to do. So start at X1, Y10, halfway down, go across to 2010, so all the way across, down to the bottom at 2020, back across to the bottom left at 120, and then close it up by repeating the first one. And again, I have to do dialect 3 to get the syntax, and I want the name back. So when we ask it this, which polygons are wholly inside the bottom half, we would hopefully expect the red one, which is polygon 4, the blue one, which is polygon 2, but not that green one, which is polygon 3, because part of it juts out of our search area. So let's run this and see what happens. So yeah, we get 2 and 4. So again, why don't we get 3? It's because we're saying what's, I'll bring this query back. We're saying what's within there. And at the minute, we don't yet support intersects. That'll be coming in the future, but you've got within or contains. So that's why 3 isn't included, because 3's boundaries are not wholly contained by our search area. Then we've got a sort of final thing that we might want to ask it. So if we go back to here and clear this, if you've ever played the game Battleships, there's normally you would just pick a coordinate. So like you would say, okay, I pick 612, and then the other player would tell you that's a hit. You've found one of their ships, or that's a miss. You haven't. There's a version of Battleships that lets you do what's called a salvo, which is like have multiple points in one shot. So imagine you've got something that can shoot multiple projectiles. They can land in multiple places on the grid. So we're going to sort of model that by saying, well, okay, I've got something bigger and I want to shoot or test a polygon that looks something like, drawing it in the blue one's a really bad idea, isn't it? Let's do it over here. That looks something like this. So I want to provide a shape and see if that shape that I'm providing is wholly contained within one of the polygons in the database. So imagine this was something like real estate and your database was full of counties and county boundaries, and you were providing the polygon of a specific house. And the question would then be, which county does this house fall into? And again, we'll look at this with maps to put it into a real world context. So what we can say here is, again, I'm doing an ft.search on my polygons index. I've got this same geometry. We're back to contains again. So does the geometry contain the well-known text? I remember when we had contains before, the well-known text that we provided was a point. So does the geometry contain this one point on the coordinate system? Now we're saying which polygon in the database entirely contains this polygon that is 1118 to 1318 to 1319 to 1119 and back to 1118. So that looks something like, what do we got here? 1118. Oh, it's in the blue one where it's going to be hard to spot. So it looks something like this. So it's a rectangle inside this rectangle at the bottom. So hopefully the answer we get is, yes, that's contained by polygon 2, which is what happens. So that's worked as expected. So this is all great, but arbitrary polygons and arbitrary coordinates have, certain field of interest. The majority case is probably where we want to do something more like the Australia points of interest. We want to find something that is on a map, and we want to draw a polygon on that map, and we want to say, find me all the points of interest that are in that polygon. Or we want to drop a point on the map and say, well, which region does this point fall into? So I'm going to switch to some code now and look at both of those examples. So let's first switch to the key browser here. And I'm going to keep all of these keys around because I don't think that's going to cause us any issues. They're all in different namespaces, so building different indexes doesn't matter. What we're going to do is look at two things to start with. So to begin with, I've got a demo where we are going to search. We're going to put a polygon onto a map, and we're going to find points of interest that fall within it. And actually, I've got the GitHub for that here. So what we're going to do is draw a polygon on the map somewhere in the San Francisco area. And our data set is going to be the San Francisco BART rail stations. We're going to find BART rail stations that fall within that polygon. And then we're also going to ask it, well, I also want stations that have certain attributes. So like you see here, stations that only have parking, or only stations that have parking. And we'll see how that works. I'll put the link to this in the comments and also up on the screen. So there's the code which you can go and play with, and let's put it up on the screen as well. And there it is. And what we're going to do is we're going to run this, take a look at how it works and what the data looks like in Redis. So let's start by bringing up VS Code here. And we'll take a look at this. So this is a Node Express project. I'm not going to sort of cover much about how Express works, but it's a framework for building web servers and APIs. And what we've got is something that serves a front end, an HTML JavaScript front end. It works with leaflet maps, and it allows us to draw a polygon and search Redis. But first, what we need to do is actually look at the data and then get it into Redis. So I've got my data here in a JSON file, and we're going to programmatically load it in. So we're not going to use Redis Insight to do that. We'll do it through a Node.js program. But let's look at what we've got. So for each station on the BART network, we've got some information about it. We've got its latitude and longitude. We've got a description of it. We've got whether or not it has parking, whether it has bike lockers, whether it has bike racks. Then we've got some information we're not actually going to use in this this example. So what city and county is it part of? And we've got that for all, I think there's 31 BART stations. So we've got that for all of the stations. And what we're going to do is, instead of writing json.set commands in the workbench to load this in, and then an ft.create command to create the index, we're going to run some code that does that. So let's quickly look at that. So this is our data loader code. It's written in Node.js, and it uses the Node Redis client. So we just import create client from Redis here, and we get our Redis credentials from the environment as a URL. And we basically just check that we've got the right parameters, read in the file, connect to Redis. And then what we're going to do is, once we are absolutely connected to Redis and ready to go, we're going to go through each of the stations in that file and store them in Redis. And what you'll see, or what you'll see this does here, is it uses the json.set command that you saw me use in Redis Insight. It's very similar in Node Redis. So we just call Redis client, which is our connected Node Redis object, .json.set, give it a key name, and then we give it a JSON path to store the thing out. So we're going to say $. And then here I'm just storing all of the things that we read out of the file. And I'm using those latitude and longitude values to create a WKT point. So here the points of interest will be represented as points, and we'll be searching for points that fall within a polygon. So that's it for our data loader. It just basically calls json.set 31 times. And then it needs to create an index over those documents, which could have been done before we did the json.sets or afterwards. It doesn't actually matter. And what we're doing here is just some tidy up to make sure that we drop any old index. You know, while I was developing this, I was changing the index schema quite a bit. And then we're going to create a new index. So what you'll see here is I've broken that ft.create command down into the strings that it represents, or that represent it. And I'm using, for the moment, what is Node Redis's generic send an arbitrary command to Redis. So in an upcoming release of Node Redis, this would be replaced by, it's got a .ft.create command, and that will understand this geoshaped spherical syntax. So there'll be a more idiomatic way of doing that than there is now. But one of the nice things about having this send command thing is you can support commands that exist in new versions of Redis that haven't made it into the client yet by doing this. So you can always do this and then come back and tidy up when the client's sort of higher level idiomatic interface catches up with it. And that's something I'll be doing with this code base. I'll be revisiting this and tidying it up. And this is the only place it needs to happen in this data loader. So basically, load the things out of the file, create 31 JSON documents, add the WKT point, and then index them is what this data loader is going to do. So if we run that, it should just be a case of can run load, and then I think it's just a file name. So data stations.json. No. Oh, no. I know what's wrong. We've not hooked this to our Redis. So we created the Redis instance at the beginning of this stream. And we haven't actually configured this code to point to that Redis cloud instance. So what we've got for that is a .env file, and it uses a Redis URL. And what you can see here is I've removed the password, which would live here, and I've removed the host name and port that would live over there. So what I'm going to do is go back to my cloud UI and get those and set that up. and then we'll be good to go. Let's go back to the Redis Cloud Console here. Looks like it's logged me out because I wasn't there for a little while. So that's good. We're back in again. And let's see what we've got. So I need this Polygon demo that we set up way back at the start of this stream. And I need to copy this value here. And I need to put that in there. So there's that. And then what goes after the colon here in this bit is the password. So what I'm going to do is take this away for a minute. I'm going to get my password and copy that. I am pasting that into there off screen. And when we bring this back again, we should have that all ready to go. So now we should be able to run this. Hey, there we go. It's connected to the cloud now. So it's storing those JSON documents for the stations in the cloud. It's created the index and it's finished. So with a bit of luck, when we go to here and we refresh this, we had Sydney and Polygon before. If I refresh this, we've now got stations. So let's do that. Okay. So we've got a whole load of stations. There might be more of them than I remember. I know why I thought 31. 31 is the number of data points in the next example we're going to look at. So, okay, there's 50 bar stations. So let's pick one. So we've got Daily City here. And as you can see, we've got everything we had in the file, but the data loader has also added, because it created this extra field, which is that WKT well-known text representation of where the station is. So there it is at that longitude, latitude. Bit unusual that there isn't a comma there, but that's how their syntax works. So we've got the data in there. And then what we'll do is we will run the Express server and kind of skip straight to a demo, then look at how that demo works. So it's running on port 4000. So if I go over to localhost 4000, what we get is this is the leaflet map. We've set it to start up centered on pretty much the San Francisco Bay Area. So this shows the majority of BART's service area, so where all the stations are. And we've got some JavaScript here that is absolutely standard leaflet maps JavaScript. And what it's going to do is every time I click on here, it's going to drop a marker. So if I drop a marker here and here, we just get markers. And the minute I drop a third marker, we've got some JavaScript that says, okay, make a polygon on the map out of those three markers. So you'll see now we have a triangle. And I can also drag them and move them around. And I can add some more like this. And now we've got a shape that looks like this. And we can make it a little bit more complicated. There we go. So we've got a shape that looks like this that we've drawn out. So what's going to happen here is, in order to ask Redis what stations fall within this polygon, I need to, let's just center it up a bit. I need to have some code somewhere that turns this into a well-known text polygon with those 1, 2, 3, 6 points. So it'll actually have 7 because you need all of them and then the first one again to close it up. It'll have all of those points in it. And then we can ask Redis with ft.search, like you saw me do before with the arbitrary polygon one. We can ask it, okay, which station lat longs map into this polygon. So let's just go ahead and actually do that by hitting search, and you'll see we get results back and we can render those on the map. And then when I click on one of these results, you'll see it's showing information that came from Redis. So it's showing that this station does not have parking, it does have bike racks, and it doesn't have bike lockers. And then this is information about the station. So keep an eye on this sort of area here up to the left in San Francisco, because if I say to it now, I I want stations that are in the polygon and which have parking. So this is a little bit like, remember when we looked in Sydney and we wanted places that were near the railway station and talked about a bridge. Then what should happen is some of these should disappear because they don't have parking. So there we go. The number of station options over this side of the bay has dramatically reduced. And if we pick on any of these now, they'll all have parking because we told it we wanted parking. And we could combine these. So we could say, I want parking and bike lockers, or I want parking and bike racks, or any combination of the three. So this is a sort of much more dynamic real world example. So what we need to do is look at how this works inside Redis with some code. So we've got an endpoint for searching things, and then we've got JavaScript in the front end that renders them out. So I'm not going to focus on the mechanics of the map here because it's all standard leaflet map stuff. But basically what happens is, let's just reset this. Every time I drop a marker, we create, or we keep a array of markers in the front end. So if I drop 4, we've now got an array of 4 markers. These have event handlers on them that allow them to move. And then we're using Leaflet's shape API, which is entirely in the front end map, to draw this semi-transparent polygon there that represents our search thing. Then when I hit the search button, what happens is we have some code in the front end that looks at the positions of all of these markers and turns them into a GeoJSON object, which is another representation of geometry. And that's something that's built into Leaflet and some other front-end tools, so Google Maps, for example. And what we do is we send that GeoJSON object to the back end, and that unpacks it, creates some well-known text for it, puts it into a Redis search command, and then the reverse process happens for the results. So an array of results come back, and we can see what those look like. So actually what I'll do is I'll open up the inspector here and look at the network tab and look at fetch. And what we'll see is when I do this search and we get those results back, you see that we did a post request to an endpoint called search. We provided a payload that looks like this. So we said bike racks, lockers, and parking, we don't care. And we provide it with a polygon. And this polygon is in GeoJSON format. So all of the coordinates are in here inside this sort of JSON path. And this is a well understood format, and there's libraries on the server side to help make that into well-known text. So we're using those. So that's what happens, what we send into Redis to search. What we get back is basically something that of our own design that we've chosen to make with the response from the search command. So I'm returning a data array, and inside that is everything that we need to plot these markers. So we've got actually more stuff than we use here. We could pare this down to just the things that we're showing. So we're not using the key, for example, in the result. We could get rid of that if we wanted to save some bandwidth. But all the things that you see, and then we're passing back this point here that then gets translated into a lat long position on the map and plotted. So that's how the front end maps work. If you want to have a look at that, the code's pretty well documented and the README is as well. So I'd recommend going in and looking at how that works. I'm going to flip to the back end and focus on the search endpoint. So over here in server.js, we have got, just really quickly, we've got a couple of routes. We've got a homepage one that deals with serving the map. It's an HTML template that pulls in a load of JavaScript that loads the map and all of that stuff. If you want to see how that works, it's contained in this static folder in here. So, and the views folder as well. So the actual page is mostly layout and buttons. And then this is it for the map. It's just a div. And we tell the Leaflet mapping frameworks JavaScript library to target that div and render the map in there. And it does that. And then it handles all of the events that we just attach event handlers to. So that's that. But we're here for the Redis bit. So let's come back to server.js. And what happens in our post search route is that we expect to find some GeoJSON for a Polygon, and we expect to find some flags for the other things. So whether there are byte lockers and parking and so forth. And we need to create an ft.search command that looks a bit like this. So it's pretty much the same as what we did with the arbitrary coordinates. So we're looking for things whose position, so the lat long points inside the JSON documents for the station, falls within the polygon that we're providing. So which stations, which are a given point, fall within this polygon we're providing. And we're actually returning more stuff than that, but you get the idea. And then the polygon that we're providing will unpack to this sort of WKT format from the GeoJSON that we're being provided with. So the good thing is there's a library in Node. You just npm install well-known. It deals with this conversion. So if this is a GeoJSON polygon, which is what Leaflet was able to produce for us, getting the well-known text out of it is a one-liner. So that's really easy. I believe in future, the search capability of Redis will just take GeoJSON as well as an option. But this is an easy transform to make. So we're doing this. And then we're also looking at those extra Boolean flags. So did they want parking? And we are basically adding search clauses for the parking field must be set to true if they did, and building up a selection of those. And then all we do is build up a search command like you saw me do in Redis Insight. So again, I'm searching my stations index. I want the position of the station, so the point in the JSON documents that we're searching, to be within the polygon that we provide. And then this acts as a sort of series of, and it must have parking if they specified that, and so on. And then again, I'm having to specify dialect 3 to enable the search support for this sort of stuff, and how many documents I want back, so the first 100. Again, you'll see here I'm using Redis, Node Redis's generic send command. So at some point in near future release, Node Redis will catch up with this functionality, and the higher level ft.search command that takes a more idiomatic object representation of the search and would deal with, oh, you're using GeoShape, so I need to put dialect 3 in. It'll do that for you. That will take over, and we'll come back and revisit this. So what we do is we run that command, and we basically just unpack the response. So you get a array of documents that match back, and we unpack each one of those, turn it into that array of objects that you see, and send it back. And that's kind of all there is to it. So we can now do much more powerful searches, in the real world, in things on the Earth here. And this polygon can be as complicated as we want. And we'll get back the stations that match. But that's only one of the types of query that we had. So this is I'm going to give you a sort of a net or a search area, and what points land in it. So this is sort of equivalent to doing the Sydney points of interest stuff, but without a radius circle now. So it's like, oh, so which things land in this particular neighborhood of Sydney would be an equivalent. But sometimes we want the opposite. We want which neighborhood is this thing in? So for that, I've got another example that we're going to switch to, and that is written in Python. There's no rhyme or reason for picking Node and Python for these. You could have done both in both, or we could have done both in Java or whatever, because all of the stuff's happening in Redis. We're just using the Redis client to send the commands to Redis and pass the responses. So we're going to switch over to a Python example now, and what that does, and I'll share the URL in the chat again, is if you are familiar with the radio in the UK, there's something called the shipping forecast. Happens a few times a day, and it's kind of like a sort of cultural reference point. And what it is it's the forecast for all the different sea areas around the UK for mariners, so people on boats. And what they do is they tell you some very precise things for each of 31 areas. And those areas obviously have defined polygons that represent them. So what we're building here is something that lets us do two things. We can drop a point on the map and say which weather area is that point in and see some weather for it. Or we could actually see now with the GIF drawing this out is drop a polygon on the map and say, well, which weather areas are within this polygon that I'm doing? So maybe like the journey that my ship's taking. Again, for now, it's within. At some point, we'll do intersects as well, which would be really useful for this, because then you could plot out the ship's trajectory and be like, which polygons am I passing through, rather than which does this area wholly contain. But we'll look at that, and I'm going to put the URL for that in the I'll put the URL for that in the chat. So there's the chat for that. And I think I've even got a banner for it. There we go. So we'll leave that up for a moment. And what I'm going to do now is close this, because we're done with being Node developers for this stream, and turn this off. And let's do, I've got this already cloned. So we've got cloned this repository here. And what we are going to do now is we've got a few requirements. So if you're a Python developer, you'll probably recognize requirements.txt file specifies the libraries and stuff that we depend on. Really, we're using Redis. We are using Flask, which is Flask, which is a web framework for Python. That's pretty easy to understand if you understand Express. And then we are using something called Shapely, which is a Python library for translating between the GeoJSON and the WKT format. So we don't have to write code to do that ourselves. I'm just going to activate my virtual environment. And if you want to follow along with this, everything's in the README if you want to do this, including how to get the Redis Stack 7.2 in Docker or in the cloud. And right, we've got that. So I now want to do OpenVS Code. And we'll look at the data set for this one. So this one, we've got all of the shipping forecast regions in our data set. And we've got slightly more complicated JSON documents. So we're sort of upping the complexity a little bit, but not hugely. And what we've got here is in each one, we've got the name again, we've got the boundaries of it. So if you remember for the BART example, these were WKT points. So stations are at a specific point in the universe. These are shapes. So it's a WKT polygon. So we are a bit like with our arbitrary coordinate system, we're going to be searching for things that are themselves polygons. And then I've put this sort of sub-object in here called forecast. And if you go listen to the shipping forecast, what they talk about for every region, and it's very formulaic on purpose, is they talk about the wind, the sea state, the weather, and the visibility, because those are the things that people in ships care about. So we've stored that. Obviously, in a real system, we would have some like service that goes out and gets this and updates it periodically, but this is just static information for a demo. And we've got that times 31 regions around the UK. So that's our data. We've got, again, similarly to the previous example, we've got a data loader. It's obviously written in Python this time. And what it does is same sort of thing. It connects to Redis. It's going to use environment variable again, and I'll remember to set that up before running it this time. And we're going to drop any previous search index called IDX regions. Then we're going to define a new one. So we're going to say, I want to create an IDX region search index on some JSON documents whose prefix is region colon. And then I want to store the name, as a tag, the boundaries as a geoshaped spherical. So that means we're using the Earth coordinate system, not a flat arbitrary one. And then what you see here is I've got some longer JSON paths. So the wind conditions are inside that forecast object in our document. So I want to look for $.forecast.wind and so on. We're not actually going to do any queries with these because it doesn't bring anything new to the table, but you can see we've set them all up in case we wanted to. So again, here we're using Redis Py's generic execute command. In the next version of the client, which catches up with this functionality, you'll be able to use the more idiomatic ft.create command and pass in a dictionary representation of this with a bunch of constants, and it will understand the syntax so that you don't have to break the command down like this. This is kind of a temporary thing. So as before, we just open the file, loop over the things in the file, and we are, in this case, pretty much just storing it as is. So we're not, in the last one, we added a WKT point because it wasn't in the original data. In this one, I've already put all of the data, all the polygons in there, so we're not having to convert them from something else. And then we quit. So what I need to do is run this, which means I need to do the thing with the environment file again. So we're actually remembering to do this before we run it this time, though. So here we go. So I need a password and I need a host name and a port. So we'll get that again. We'll go back to Redis Cloud, which I'm sure hasn't logged me out again yet. We've not been too long. Right. So I need that. So there, you'll notice here there's an extra decode responses equals true. Let me just get the password before it times out and talk about that. So decode responses equals true here is the Python client. If you don't pass it this, it doesn't decode things from Redis back to strings. So things will stay as sort of byte arrays, which you might want if your data is of that format, or you don't want to spend the time decoding it in the client. I do in this case because I know everything's basically a UTF-8 string in there, so I've turned that on. So I'm just going to vanish this again and put a password in there, which hopefully we get right, and hopefully it works again. Okay, so that's all good. So what we should do now is we should be able to do Python data loader.py, and it will probably tell me how I set it up. Yep. So load, and then it's data / forecast region.json. So let's load those. Off it goes, and this will be the one with 31 items. So that's where I was confused earlier. So we've got 31 items. Created the index. If we go back to trusty Redis Insight here and refresh our key space, what you'll see is I've got stations for bar, I've got Sydney for the Australia example, I've got regions for this one, and I've got polygons. This, just to make it very clear as well, this sort of tree is not how they're stored in Redis. So they're stored flat like this in Redis. But a really good key naming tip is to use a colon or some other separator between like prefixes on your keys so that you can sort of namespace the key space and work with it more. So like everything to do with the stations application began with station. So they're really all in the same flat space. But when we hit the tree view here, Redis Insight interprets this as the colon or some other configurable character that you can set being like the namespace delimiter. So it treats it like a tree structure, and it's just a lot easier to rationalize and demonstrate like that, and also to manage. So if we go into the region here and click keys, you'll see we have all of these regions. If we go to 40s, there's a region called 40s. You'll see that we've got its polygon, which is the thing we're going to search it by. And then in here, I can expand out this JSON sub-object which has got the 4 things, which are indexed, but we're not going to use them in our example. That's what our data looks like. Now what we need to do is go ahead and run the server. And let's see what port this one was set to attach to. Oh, 5,000, okay. So let's see what we've got here. So now we've got a map that, again, similar sort of thing. It's a leaflet map. There's JavaScript and events for that, and it works in roughly the similar way. So we can now do 2 sorts of query. So what you saw me do before was drawing a polygon on the map for BART stations. So I can absolutely do that here. And I can hit search. And what I get back is you'll see it's drawn in the polygons. So not points like we have with stations, but polygons, because these are areas. So these are the shipping forecast areas that are wholly contained within the red polygon. So I can hold or hover over here, and we've just got some code that detects that event and basically displays information that came back from Redis. So, you know, the name of the thing and the 4 things that mariners care about. So I can do that. I can expand this out here a bit and give it some more things. And we can see what is maybe in this region. And you'll see we've got probably pretty much all of them now. As the UK is entirely surrounded by polygons. So these are all the different weather areas. So we can have a look at what things like down in the Wight area off of the Isle of Wight in the Channel, or Dover, or Thames, where the River Thames comes out, and so on. So here we're searching in a polygon, and the things that we are searching for are polygons and their areas on a map. So again, this might be useful for things like which electoral wards fall in this polygon, or which delivery areas if you're a mail service, or whatever you've got the data for. So that's one sort of thing we can do with this. The other thing that's different with this example is I can pick a point on the map here, just a single individual point. So let's do one there near the Isle of Man. And if I don't do anything else, I can actually search for this. So before, when I had a polygon, we were saying, oh, find me all the things that are contained by this polygon I've drawn. Here we're saying, I've just put a point down. So if I do search, what it's doing is it's searching for which polygon in the weather regions part of Redis contains this point that I'm provided. So I've picked a point that is in the weather region called Irish Sea there. And you'll see if we move it to reset that and move it to over here somewhere, we'll get something different. So now I'm in the Wight region. So we can basically say, you know, if my ship's in this location, which weather region am I currently in? What's the weather like for me? Or we could go ahead and draw a polygon that covers like pretty much the whole of the Channel area here and say, well, I've got to pass through this area. Which regions am I passing through? And I'm passing through Portland, Wight, and Dover in this case. So those are the 2 sorts of searches that we can do with this sort of data. Again, I'm not going to focus on the map, so I'll go back to the Python. Let's bring the inspector up. The way that the front end talks to the back end, pretty much the same. So if I just run this search again, you'll see that what we do is we hit an endpoint called search and we post to it and we send it a payload, which is a GeoJSON format polygon, because again, that's easy for the maps library to create. And what we get back is a data array of all of the polygons to plot. And this time I've turned the polygons to plot into GeoJSON on the server. So the front end doesn't have to deal with well-known text at all. It just deals with GeoJSON, and Leaflet's got methods to build polygons from a GeoJSON representation. So we're doing a little bit of translation work on the server, which we'll look at. So let's close the data loader. Again, I'm not going to demonstrate how Flask works, but it's pretty much the same as Express. So if you understand one, you can look at both examples. There's a static folder in here, and that's where the CSS, the images, the JavaScript for the front end, and the homepage template are. It's the same deal of there's an empty div where the map gets drawn, the map's JavaScript loads, and it takes over and handles events, and we write callbacks for those. So nothing Redis related in there. The server is in app.py here, and we are using, in this case, a library called Shapely to do translations between GeoJSON and WKT formats. We connect to Redis, like you saw in the data loader. Our home route just serves the HTML, so we won't even look at that. And what we're interested in is this search one. So this is where the data comes in from the front end, and we then do a search for whatever we've got. So there's two sorts of payload we can receive from the front end. Either I've drawn a polygon or I've just got a single point. So when it was a single point, I just put that in a field called point in the post, and the point's got a lat long associated with it, and we can basically just build a simple WKT string of that. So that needs to be point, brackets, the longitude, space, the latitude. And in this case, we want the operator contains. So we want to know which polygon in the database contains this point we're searching for. In the other case, we send it a GeoJSON polygon from the front end, and we have to turn that into a WKT one. So that's pretty easy to do. We just use a couple of lines of code from the Shapely library that deals with all of this stuff for us, and then we get the WKT string for the polygon, which, if you remember, looks a bit like this. It's polygon, double brackets, and then all of the points in the polygon, with the first one repeated again at the end to close the polygon. And this time we're doing a within search. So we want to say, we've been sent a polygon, so we need to know which polygons in the regions in the database are contained within this one that we've been sent. And much in a similar way to the Node code, it's pretty much exactly the same. We use currently Redis Py's generic execute command because the geoshape syntax not quite implemented in the released client just yet. So when this is, it'll get replaced by the more idiomatic ft.search command. For now, we can kind of use the run an arbitrary command option and just form up that search command we want to send. So like you saw me doing in Insight, we're saying, I want to search in the regions index where the boundaries of the thing is within the well-known text we're providing. And I want the first 100, and again, dialect 3 to specify the that we're doing this GeoSearch stuff. Again, when this makes it into the client, you won't have to worry about low-level details like this. And then the rest of it is just parse out the response from Redis with one additional step. So what we get back from Redis, because we stored them in there, is where the weather areas are as WKT polygons. Leaflet doesn't understand that directly for rendering them. So what I'm doing here is just turning them into GeoJSON and before sending them to the front end. So we don't have to do lots and lots of parsing in the front end. Generally, the server is a more powerful environment to do that. And also it means that as far as the front end is concerned, it's GeoJSON in, GeoJSON out. If this changes in future, because search can support GeoJSON directly, no front end changes required. So again, we'll revisit this in the future. And then we're just sending that data array back. And that's kind of it. So let's just quickly look at what the payload looks like for when we just send the pointing, because we didn't really do that. So I'm going to start the inspector here and click on that point in the Isle of Man again and do a search. And what you'll see is, here's my search request, post to the search. So here, what we're sending is not a polygon. We're sending this key called point, and it's just got a lat long in it. And that was how our code up here knew what sort of search to do. So request.json contains a key called point, and then we build up WKT that looks like this and uses the contains operator, as opposed to one that looks like a polygon and uses the within operator. So, and then we find that that's in the RHC, which is kind of where we expected it to be. So yeah, that was everything I got. So I have already put the URLs for this and this demo inside the description on YouTube for this. I will also subsequently put the link to this YouTube video in the READMEs for this, so they're self-contained. So if you want to go and play around with these, all of this stuff is available to you right now to do so. And then as we release the clients with a more idiomatic interface for this, I will come back and update this and do another stream on it. So for now, that's kind of everything. I think the only thing that remains is to say, well, where can you talk to us about this in between times? We have a Discord at discord.gg/Redis. And what you'll see is we have, well, we advertise events that are on, and this event's on right now. But we have channels for all sorts of things. So you can show off your projects. We love that when people bring us stuff to and they want to share. You can ask us questions. There are channels specifically for search. So search here that we are using. This is the feature we're using today. There's also, if you want to talk about Node Redis or other JavaScript clients, so one of the other things we use today, there's a channel for that. And we'd love to hear from you, and don't be afraid to ask us questions. There are both staff and other community members in the Discord, and we will do our best to answer you. So yeah, that was it for now. I'm going to just turn off this, and obviously as well, if you're interested in more of this sort of stuff, take a look at our YouTube. We generally stream to there periodically. And we generally announce when we're going to do that, both in a Discord event, and we also have a page here where you can usually see upcoming events and also all of our previous events with all of the videos. So if you want to scroll back and see what we've been up to, you can do that. If you'd like to learn more about Redis, then Redis University is a good place to start. It's university.redis.com. It's absolutely free and online. And there are courses for all sorts of things. So relating to the content that we talked about today, there are 2 courses that use the search capability of Redis Stack, one that uses JSON, and then there are courses for Python and Node.js developers specifically. But don't think that you're just limited to those. Those are the languages I chose to do today. We could have done this demo in, say, Java and .NET if we wanted to, or PHP and something else. The same principles on the server apply. It's just how your Redis client, so the adapter between Redis and your programming language, chooses to implement the commands that changes. But I went for Python and Node, but again, feel free to run through the code. And if you don't understand anything, you want some help, or you find a bug, then come find us on Discord, or just raise an issue in the repo and tag me, and we'll see what we can do. Right. That was it for today's live stream. So hopefully you have a good rest of the day wherever you are. It's 3:30 here in the UK. So I'm going to go back to the rest of my workday. Thanks very much, folks. Bye.